Hi guys, so we're going to continue with volume today, and you can see from today's aim, it's called What is the washer method and how do we use it? So before we talk about the washer method, let's talk about the method we've been using so far. So in our previous couple of lessons, we've had some function. Let's say this is like y equals square root of x. And we take it, we have an area that we bound, so you could see the area that I've shaded in, and then we take it and revolve it around either the x or the y-axis. So here, if we revolve it around the x-axis, we would get a shape kind of like a bowl, right? And if we cut out pieces of it, they would be little discs. So there'd be discs there, and a disc there, and a disc there. There'd be an infinite number of discs that we cut out. So another nickname for this method is called the disc method because when we cut it into little slices, we would get discs. But let's look at this a different way. So let me erase those. All right, what would happen if we revolve this around the y-axis instead? Would we still get little discs? So let's see. If we did that and we created a shape, we'd have something like this on the other side. And sure, I would say like over here, we'd have a disc. But would we have a disc over on the other end, like over here? And remember now, a disc is a fully filled in circle. So would we have circles really? And the answer is no, we wouldn't really, because there'd be this centerpiece that's missing out of our circle. Because we can see that from this area being rotated, we have this area as well, but there's nothing in the middle. So this is no longer a disc. This is actually something that in mechanics is called a washer. And it's basically a circle with a hole cut out of it. So sort of like a donut. And we use washer method when we're rotating a shape, but then there ends up being some empty space in the middle. Now the way we do this is going to be very similar to the way we did area between curves. So let's take a look at an area example. If we have, oops, remember from our lessons, let's say if we had x squared and we wanted this area, sorry, not x squared, square root of x. And then we had x squared and we wanted this area. And then we wanted the area between them. So we had that and this. Now, we knew this, which is the same as this. We knew this, which is the same as this. So it makes sense that we would just subtract the two to get to the area between these, the area that is not shared by both. And you did something very similar in your starter as well when you had a cylinder with a hole in it. My assumption is that you found the volume of the large cylinder and then subtracted what would have been the volume of the smaller empty cylinder inside. So we're going to do the same thing for these problems. So let's look at example 1. We have the two functions that I just used for area. We have y equals square root of x and y equals x squared. But now instead of finding area, we're going to take this area bounded and revolve it around the x-axis. So what's going to happen is we have this area between these two curves, and we're going to revolve around the x-axis. And it's going to look something like this. Now, you should be able to move this graph around, but for some reason my computer's acting up and it's not letting me. But if you move it around, you're going to see that the inside, you'll be able to see into this bowl-shaped object. It's not a solid bowl. It's like a real bowl now. So there's an empty space. All right, So then we're going to need to subtract one function from the other. So to do that, we have volume equals. Now our basic volume formula was the integral from x1 to x2 of pi f of x squared dx. So first, are we still going to use x's? Because remember, we also learned about y's. In this case, we are still going to use x's because we are revolving around the x-axis. Whenever we're revolving around the x-axis, we use dx, we use x's for our limits, etc. But for this volume, we will be subtracting a second volume, the one that leaves this inner space here that's going to be empty. So we are subtracting same limits, which is nice. So x1 to x2 of pi g of x squared dx. Now, since these are the same limits, we can combine this all into one volume integral. So integral of x1, x2. They both have pi, so we can actually factor that out. And we'll have f of x squared minus, second bracket, g of x squared dx with a pi on the outside, because if we distributed it, they would both get the pi's, like we can see in this first line. All right, so let's fill these in. Now the pi, remember pi is a constant and it's a multiple, so the pi can really just come out. It doesn't even need to be in the integral. x1 and x2, well, we can see that this starts at the origin, so our x1 is going to be 0, but our x2 is where the intersection of the two functions are. So we should just figure that out. If you can do it algebraically if you want, wherever square root of x equals x squared, but that's going to be at x equals 1. All right, now it does matter which order these go in, just like with area. It works the exact same way. We have to think of what's the greater function, or really what's the function that's going to create our outer circle. Is it going to be x squared, or is it going to be square root of x? And in this case, it's going to be the square root of x. If we revolve this, this would create the outside of our bowl shape. So that is our f of x. So square root of x squared. And then we'll subtract x squared because that will create the inside of our bowl shape. X squared squared dx. Now for this packet, I want you to keep continuing to practice your integration. So please do these by hand. They should be not too difficult, but let's see. Let's actually square these. So we'll have x minus x to the fourth. Forgot my limits of integration. And this is a fairly basic integration problem. X integrates to x squared over 2. X to fourth integrates to x to fifth over 5. And you'll integrate this from 0 to 1. Remember to substitute in. So pi of 1/2 minus 1/5. And if you substitute in the 0, it would just be 0. So there is your answer. And if you happen to simplify, this simplifies to 3/10 pi, but remember, simplifying is often dangerous and I suggest avoiding it. All right, let's do one more problem. All right, find the volume bounded by these graphs. And I gave you a graph so you can make a sketch and see what you're doing. Let's see, y equals x, that's a line that looks like that. Y equals x plus 1 is the line parallel to it and above it. So x plus 1. Then x equals 0 is the y-axis, and y equals 2. So this was y equals 1, because that's the y-intercept there. Y equals 2 will be up here. So we want the area that's bounded by all 4 of these functions. So boundary, 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 boundary. This is the area we're going to revolve. And we're going to revolve it around the y-axis, so this way. So if we revolve it, we'll have a shape on this side that's going to basically be a reflection, except remember, this will be 3D. So really, this will be going around. And look, we're going to have this empty space in the middle, while everything else is filled. We'll have the emptiness, this little empty cone in the middle. So this is going to be washer method again, and we'll have to subtract these two functions. All right, but also, since we're revolving again around the y-axis, we know we need dy's. So if we're going to find a volume, we're going to need a y1 to y2. I'm just going to put the pi outside because we know that's a constant multiple and the integration doesn't affect it. Now we're going to need the larger function squared minus the smaller function squared dy. So let's see what causes, let's see what we can fill in with these. All right, y1, well, again, we start at the origin, but the outermost part of our shape is here. That happened at y equals 2. Remember, that's what we created this boundary at the top. So y equals 2. And now between these two functions, so this function and this function, what created the outer part of our shape? It's the x function, this one, because that is what creates this, the outside of our 3D figure. Now, the other thing we need to do is these are dy's, so we can't write x here. We need everything to be terms of y. So remember, oops, erase. This equation was x equals y. So instead of writing x, we could write y and have that be the same thing. And remember, we need to square it because this is a radius squared. So that leaves the other function as the inner, but we can't write x plus 1. We need to write it in terms of y. So y equals x plus 1, but that means x equals y minus 1. And that's what we need to write here because this is a dy function. So now we have this. We're going to have to do a little expansion right here. And distribute our double distribution. Because remember, this is a function. If you want to, you could use u substitution, but I find it easier in this case to expand it. And now we can integrate here, or actually notice how we have y squared, and it's a subtraction. So these two are going to go away. So then we'll have 2y minus 2 dy, and we can integrate here. We'll get y squared minus 2y from 0 to 2. Forgot my limits of integration up there. And then, of course, substitute in 2 squared minus, just realized I made a mistake. This should be a 1, so that's a 1. So plus 1 minus 1. Y squared minus y, so 2 squared minus 2 minus, if we sub in the zeros, we're going to end up in this case with all zeros, and there is our answer. All right, so again, make sure you email me if you have any questions. Please finish the whole packet without a calculator. I want you to practice your integration, and I will see you during our period.